told everybody there is no mask, so we could have a bigger audience. And Peng even has some videos, but next time we'll be smart about this. So without further ado, I'll give a quick introduction to what we want to say. We just want to be of a little bit help. That's the goal of me giving this talk. So it's called a meta-analysis of COVID-19 related combining of multiple omics data sets, but it doesn't have to be COVID-19 related. It could be anything. So first we talk a little bit of background, motivation, and then we talk about how to calibrate between the RNA sequencing and RNA sequencing data sets from 2 different labs. Of course, we can do even more than 2. That's the idea, right? And then we will also talk about something we did before, which is to calibrate between RNA sequencing and microarray. So the idea is even we could do that. Absolutely, we could do the RNA-seq and RNA-seq, right? So then we will introduce our team and collaborators. So here is some background and research question. So the calibrating between the RNA sequencing data. I'm especially glad that we actually have a lot of scientist friends from chemistry and other departments. And that's very helpful because this is useful to them. We probably already use it. So basically, because COVID is such a big public health problem, we have a lot of open data set. The organization of the NIH is very good at this website, and it's a searchable database. You could search, so we searched some RNA sequencing database, and we found some which is already in the GeoData Bank. So here, I'm only going to use this as an illustration, but you can say, our goal here is not to provide all the medicals, all the other details, but just to tell you some basic statistical methods you can find useful. So these 2 data sets, they are based basically both plasma leukocyte. So at least they are comparable in terms of that. One data set, they have 100 COVID-19 patients, 50 in ICU, 50 not in ICU. And then they have 26 non-COVID control subjects, so-called, and 16 in ICU and 10 not in ICU. And this is not all, this is always a worry, because we really don't have all the covariates on these controls, but they have tried their best to provide a lot of information like gender, age, and all that. And we could even acquire for more if we get in touch with the collaborators. They already have their emails on this website. So I'll make sure you have my talk. So the other study is very small. The other study only have 7 patients in ICU and 7 non-COVID controls, also in ICU. So we thought, we're gonna start by try to calibrate between these 16 controls in ICU and these 7 controls also in ICU. What do you think the data will look like? Okay, but before we do that, we show that. We say that we did some pre-processing of this data. So at least they have gone through the same normalization methods. We know there are typically 4 and there are more, but we are not going to have a detailed discussion here. It's not time. Okay, all right. So what we do is we basically take the mean of each gene for each data set across the subjects. Then we take log2 of the gene means and plot them against each other. As you know, this regression terminology, I shall not repeat. So basically here we have 4 typical candidates. They are all non-parametric regression lines. And that means you do not need to have any normality assumption, which do not hold in this situation, even we take log2 transformation. So this red one is the most typical one. This is the ordinary least square regression line that we have learned when Y is the response variable. And then this green one is also ordinary least square regression line with X as response variable, because the thinking is it's basically arbitrary. which one is X, which one is Y. So basically they both have measurement errors. They are in equal positions. And in between, you say this purple one is the geometric mean regression line. And this yellow one is the orthogonal regression line. And those are two of the very typical common lines we use when they have errors in both variables. So when they have errors in both variables, it's not a good idea to use the green or the red. Okay, and then here we also show the reference line of y equal to x. So in the ideal world, they should be very close to y equal to x. But of course, we are not in ideal world, they are not very close. As you can see, all these gray dots, they are the log2 mean of the gene pairs from the two studies. And these are only the control subjects. So the question is, which line to use? Any volunteer to tell us which line to use? It's okay, you cannot be wrong. I told you, do not use the green or the red. And yeah, actually, later we will show you the two in between, they are good. They are both good in this situation. Now the story is, actually, these four lines are not the whole story. In fact, you see, they all pass through a common line, common point right here. Now, what is this common point? I know many of you know this common point. This is X bar and Y bar. So they both pass through this point. Now, ranging between the green and red lines, there is an infinite many regression lines. Each one is a good candidate in a way, all right? So that's the problem, okay. But so these lines we showed you are just the very typical ones. So we will just have a very simple review as promised, very little math. And you will actually like these maths because they are very intuitive. So by only assuming the variability in the y direction, we can minimize the sum of the squared vertical distances from all the points to the line. And that regression line is the ordinary least square line. Sometimes we just call it least square regression line, all right? So the other one is then they assume no variability in y, only variability in x. So minimizing these squared horizontal distances, that's the OLSX. But then they both have some problems because both have variabilities, x and y. So one compromise is to take the perpendicular distances, okay? And then we square it, we sum it up, and we find the regression line that will minimize this sum. And that's the orthogonal regression line, okay? And so this would be the slope of the orthogonal regression line. Now the last common approach is the geometric mean regression, which you can obtain the slope by using the fitted two ordinary least square slopes. That's one way to do it. But you can also have a very simple geometric, very simple geometric interpretation. This line actually would minimize the summation of the summed areas from each point to the line. So this is a perpendicular, this is the vertical distance, this is a horizontal distance. So here's a 90-degree triangle. Okay, so, and you can imagine each of the points will form a little triangle areas. You sum up these areas, you minimize that. That's the geometric mean regression line. So I'm sure, I hope these bars are not affecting your view. Okay. So many years ago, actually, truly many years ago, we had a collaborator who is not a medical doctor, who is an environmental scientist at Brookhaven National Lab, Larry, Dr. Larry Kalman. And Larry wants to identify the linear relationship between the concentration of carbon monoxide and some organic aerosols above Mexico City. And he actually was quite knowledgeable. He knew about orthogonal regression line, geometric mean regression line. And then he asked me which one to use. And to me, at that time, it was a good question. I didn't have an immediate answer for him. Okay. So in fact, he was not alone in that question. As Dr. Edwin Jeans, physicist, said in his book, Probability Theory, The Logic of Science. He said, the most common problem of inference faced by experimental scientists is linear regression with both variables subject to unknown error. And now sometimes you want to have a nonlinear relationship when both variables or more variables are subject to unknown error. So I mean, this is the line of research we are doing, all right? So today we only introduce this part. So for given two measurements, which errors in variable regression line, we call errors in variables because both variables have errors, is the optimal line? It actually depends on the ratio of their measurement error. Now, the thing is, we can actually correct this problem from the design point of view. Many times, my collaborator would ask me, Wei, do I need replicates in my study? You know, RNA sequencing is so expensive. I mean, I can't afford many replicates. Sometimes we can only afford 3 subjects. You know, that's the situation, right? So usually we do not get our own replicates. If we have a replicates, like the same sample, we ran a few times in the same machine, we actually could compute the errors, right? We even can compute errors for each genes, but usually we do not have that luxury. But if we do have this from both platforms, this ratio of the errors in the y direction and the measurement errors in the x direction, each of these lambda will correspond to a unique one among those infinitely many errors in variable regression lines ranging between the 2 ordinary least square lengths. You actually can find the optimal one. The extreme case would be when lambda equal to 0 and infinity. Those are the 2 ordinary least square ones. And then the other special one is also the orthogonal regression, when the variabilities are equal, all right? And then the last one is the geometric mean regression, when the, when there is no other errors except the ones from our measurement. Actually, there are sometimes some hidden errors we couldn't measure, all right? So this is also a special case. But still we have a problem, because if we do not know the error variance or the ratio of it, then we don't know which line is the best. Okay, so we tried to do some research, and so it took a couple of years to do the research, and then another couple of years to have the research published. All right, so we basically developed 2 classes of non-parametric regression lines for the whole families of infinitely many regression lines. One system we call the compound regression line, the other called constraint. Here, today we only talk about the compound, which is very intuitive. You can see it's very intuitive. Basically, this whole class is a linear combination. We have a distance. We always have to have a distance measure, right? Then we try to minimize this distance measure. Then we get to the optimal line. And this distance measure is simply a linear combination of the sum of the squared vertical distances and the horizontal distances. And this weight, gamma, can range between 0 and 1. And of course, at 0 or 1, you get the OLS on y or x, respectively. Okay, so that's the idea. And so, but as you can see, R range from 0 to 1 for all real numbers. There are infinitely many of regression lines, errors in variable regression lines. And the good thing about this approach is totally non-parametric. We do not need to worry about any parametric assumptions. And so this paper was just published last year in the American Statistician. And see here, Ling Leng, that's my former PhD student. She's now at Google. So here we illustrate some important result we obtained from this systematic study of the properties of the errors in variable regression lines. This surprising is the GMR has some very nice properties. We did not anticipate this at the beginning, all right? We were thinking, OR or GMR, should we normalize the data before we do it? But when we finished the derivation, we were surprised. You can see this is a very simple data set from a statistical textbook. Again, these are a few points, and all the lines ranging between, here's OR, here's GMR, and the passing between the mean X bar, Y bar right here. And we designed a type of efficiency plot. Okay, we basically try to measure for each errors in variable regression line, you see, which is given by this gamma. You see gamma range from 0 to 1, right? And for each of these gamma, we want to say how accurate is that line in measuring the y, which is denoted by this curve E1. And the other curve is E2 is the accuracy in measuring x, all right? As you can see here, we have an interception. This intersection is geometric mean regression. We were really surprised, and it is, we didn't anticipate. And then they actually gave this regression line, GMR, gave equal efficiencies or accuracies for measuring both x and y. And not only that, it also gave the maximum sum of accuracies for measuring x and y. So that is very nice. As you can see here, here is the yellow one is the GMR. As you can see, equal efficiency for measuring x and y, y and x actually. And their summation is 1.5, which is bigger than the OLS, which is only like 1.24 or the other one. And it's bigger than the OR2, which is right here, which is 1.43. So really optimal, not only for this data, for all the data. So this is one of the theorem we derived. It says, again, summarize. Geometric mean regression will always yield equal efficiencies for the estimation of x and y, and it will always maximize the summation of the two efficiencies for x and y. So with this in mind, now we actually can answer this question, right? So again, given these infinitely many choices, not only these four actually, we know that if we have no idea about the error variances, we can absolutely choose GMR, which is always optimal when the variance ratio is unknown. Now, the thing is, because this is RNA sequencing versus RNA sequencing, they are the same measurement platform, right? They are same kind of equipment, even not the same equipment. So it is plausible to think the error variances are pretty equal, all right? As actually we observe right here, you can say this purple one is GMR, this yellow one is orthogonal regression line. They are very close. Okay, so actually that gave us a good feeling, right? These data are not as bad as these gray dots are showing, right? So we could use either in this situation, either GMR or OR to do the calibration. So once you have the regression line, for example, you get this relationship, then you can transform you can transform the disease subjects according to this, the X transform in this way, so it will be comparable to the Y. Then you can combine the data together to do meta-analysis. So the other way to derive the baseline is to actually also use the parametric approach. In this situation, actually we could do it because we usually assume the RNA sequencing, the count follows negative binomial. So we actually in the middle of doing this, and next time we can show you the result. But I can assure you that that regression line, which we'll call GEIV line, will be very close to the GMR line. All right. Now this, also previously we have done some calibration work between RNA sequencing data and microarray data. Given so many years I've been at Stony Brook, actually going to 25 years very soon. I've been working on this, and we had only microarray data before, and then suddenly we have RNA sequencing data. And the thing is, for all those millions, $billion of data, can we just drop them, or can we still use them, right? You see the GL data sets, you know we have this urgent question. So the good news is we could calibrate these two types of data sets very nicely, as I show you right here. This is one of the data set. I will keep it a secret. You call UHR. I think it's one of the public data set we used before. As you can see here, I showed you the parametric optimal GEIV, which is blue line right here in the middle, also passing through X bar, Y bar. And you can see the GMR, the purple, very close to the blue line, right? And also the OR is also very close, right here. But here I would rather use GMR than OR because it's two platforms. One can never be sure their measurement errors are comparable. So I don't think OR is very justifiable here. But GMR is. And this is another data set. You can see This is a GIV, this is GMR. Again, you can just use this to do it. So finally, big thanks to my team. They are my current and past PhD students. Right now we have Ms. Zhao Yan Liu, Mr. Tian Zhu, and Ms. Yuan Tian working with me on this. And previously I had students, Dr. Ling Leng and Dr. Yuan Hao Zhang. They have all graduated and working in companies now. And I also want to thank all my collaborators, mentioned here or not even mentioned here, who have motivated us directly or indirectly to do this line of work. That's Dr. Wadi Baho and his lab, and Dr. Ellen Lee and her lab, and Dimitri and Larry. Thank you very much. And I mean, these are the, we try to be